Welcome to the Remediation Deep Dive, your source for distilled, impactful knowledge in environmental remediation. We break down the science, the strategies, and the story shaping our field so you can stay sharp, informed, and one step ahead. I'm Max Flux.
And I'm Sandi Loam. Today we're taking a deep dive into a really interesting paper. It challenges some of the ways we usually think about environmental cleanup.
Absolutely. Our focus today is on PFAS Monitored Retention, a framework for managing PFAS-contaminated groundwater sites by David T. Adamson, Charles J. Newell, Poonam Kulkarni, and Hans Struve.
Quite the lineup of authors there.
Indeed. And our mission for this deep dive is to really unpack the natural mechanisms that hold on to PFAS within an aquifer. We want to explore how these built-in processes might actually stop a PFAS plume from getting to wells or rivers.
Right, and we'll also get into these new concepts they've coined, PFAS Monitored Retention, or PMR, and PFAS Enhanced Retention, PER.
Exactly. It's so important because, honestly, PFAS remediation often feels like we're in some kind of bizarro world, doesn't it?
It really does. You've got these incredibly low limits, parts per trillion, and, well, no proven ways to destroy it in situ in the ground itself.
And it all comes back to those super strong carbon-fluorine bonds, making PFAS just incredibly persistent.
And mobile, too.
Yeah, highly mobile. So the old standbys like pump and treat or even injecting sorbents sometimes, they just don't cut it for every PFAS site. They can be overwhelmed.
We've definitely needed something different in the toolbox.
And that's exactly where this PMR idea comes in. It's kind of an evolution from monitored natural attenuation, MNA, which many listeners will know.
Okay, but how is it different from traditional M&A?
Well, M&A usually relies heavily on microbes breaking contaminants down from biodegradation. But with PFAS, PMR focuses more on the physical and chemical retention, holding it back, slowing it down, without necessarily destroying it right away.
Ah, so less about breaking it down, more about pinning it down. Containment using nature's own mechanisms. It's about managing the risk by limiting mobility. And it can be a really sound, scientifically defensible, and frankly more economical approach for certain sites.
Especially where maybe the plume isn't directly threatening a drinking water well right now. Or maybe as a stopgap.
Exactly. Or as part of a long-term solution.
Yeah.
So let's talk about how the aquifer holds on to PFAS. One big way is sorption.
Okay, sticking to the soil particles.
Yep. You get hydrophobic interactions, basically, PFAS avoiding water, especially with the longer chain types, and electrostatic forces, too. But what's really interesting is the role of the air-water interface in the unsaturated zone.
The space between the water table and the ground surface.
Right. Some studies suggest that accumulation right there at that air-water boundary can account for like 50 to almost 80% of the total PFAS retention. It's huge.
Wow, so it's not just the soil solids, but the air pockets too,
Yeah.
actively trapping PFAS. That's unexpected.
It is, and it makes a big difference. Another key mechanism is matrix diffusion.
Diffusion, so moving into tighter spots, like clays or silts.
Exactly. PFAS molecules slowly diffuse into these low permeability zones. Now, for many contaminants, we see this as a curse, right? It makes cleanup harder because the contamination bleeds back out slowly.
Yeah, the dreaded back diffusion.
But for PFAS, because it's so persistent and hard to destroy anyway, this slow diffusion into tight zones is actually a bit of a blessing. It effectively removes mass from the faster-moving groundwater pathways.
It slows the whole plume down.
Dramatically. They cited an example, AFFF Site 1, where something like 82% of the total PFAS mass was estimated to be stuck in these lower permeability soils.
82%. That's a massive amount being naturally contained.
Yeah.
Okay, what else contributes?
There's also chemical retention, which often involves precursor compounds. Many sites have these polyfluoroalkyl precursors that aren't PFAS yet, but they transform into PFAS over time.
So they act like a temporary storage.
Kind of, yeah. They're often less mobile initially, so they delay the release and migration of the final PFAS products. And this transformation can be slower in anaerobic, low-oxygen conditions.
Interesting. And I guess simple dispersion plays a role too, just spreading out.
Sure, dispersion helps dilute the plume and reduce those peak concentrations as it moves. It all adds up.
Okay, so we have these mechanisms: sorption, diffusion, precursors, dispersion. How do site managers actually figure out if PMR is a good fit for their site?
Good question. The authors propose a structured framework using lines of evidence, or LOE. LOE1 is about the numbers quantifying the plume mass discharge and, crucially, the travel time to the nearest receptor.
Like how long until it reaches that river or well?
Exactly. They suggest if the travel time is, say, 10 years or more, PMR starts looking pretty favorable.
Makes sense. And LOE2?
LOE2 is about demonstrating these retention processes are actually happening in the field. So you'd collect soil samples, especially from those low permeability zones, to show PFAS mass is indeed accumulating there.
You need the field proof, not just modeling.
Right. And they suggest a tiered approach, tier 1, 2, 3, so you can tailor the investigation effort to the site's complexity.
Okay. But what if the natural retention just isn't quite enough on its own?
That's where PFAS Enhanced Retention, or PER, comes in. This is where you give those natural processes a boost.
How do you do that?
Well, common examples include things like injecting particulate sorbents, think colloidal activated carbon, CAC, that's already being done widely to create underground barriers, or maybe installing caps to limit infiltration.
Ah, so you're actively tweaking the site conditions to make sure PMR can work effectively long-term.
Exactly. PER is designed to help shift a site into a state where PMR becomes viable and protective.
Let's loop back to that AFFF Site 1 example. How did PMR look there based on this framework?
It looked really good. The estimated PFAS mass discharge leaving the source was only about 0.31 kilograms per year, pretty low. And the travel time to the receptor, which was a big river 800 meters away, was calculated at around 40 years.
40 years. Okay, with that kind of time frame, relying on monitored retention makes a lot more sense.
Absolutely. It provided strong evidence supporting PMR as a suitable long-term strategy for that specific site context.
So wrapping up, this PMR concept feels like a pretty significant step forward, offering a more practical, maybe sustainable option for some of these challenging PFAS sites.
I think so. It gives us a scientifically sound alternative for lower risk sites, moving beyond the idea that aggressive intervention is always the only answer.
Well, that's all the time we have for this deep dive. We certainly hope this has given you some valuable insights in the complex and evolving world of PFAS remediation.